Okay, so that was chapter 4. Any questions on chapter 4 before we start in on our next exciting chapter of study? You gotta go for a walk first?
Throw up.
Oh, go throw up. There you go. It's called reverse peristalsis. Sounds more scientific.
How do you supposed to work power before that?
Power, reverse peristalsis. It's got to be. Mega. Okay, so we skipped 5. We're not going to disregard 5. We're going to tack it in at the end of the semester 5 because it's kind of an easy chapter, and if I have to cram that one down your throat, I'm not really too upset about it. But chapter 6, bones. What kind of tissue is bone? Connective tissue. So what we're going to find when we talk about the skeletal system, which is chapter 6, bones and skeletal tissue, is it's not just going to be bone or osseous tissue that we're going to discuss in this chapter. It's also going to be cartilage, because that's also part of your skeleton, believe it or not. Bone is actually made from cartilage. So when you started out as a tiny, tiny group of cells, the first tissue that came into play before your bone came into play was cartilage. So when we talk about the skeleton, we're going to divide it into 2 major parts. If I crammed a rod down through the top of your head and spinal cord, which would be uncomfortable, everything that hung off of that with respect to your skeleton would be that central portion. That's called the axial skeleton. And then everything that hangs off of that is your appendicular skeleton. So in this diagram, we see those cartilage materials that are also associated with the skeleton. So you can see that the axial skeleton is kind of that dark beige, and the appendicular skeleton is the light beige. And then we see several different types of cartilage also found in different places associated with the skeleton. Elastic cartilage we find in my ears that bounce back nicely. We find hyaline cartilage covering the ends of bones. And we're going to learn that the name for the ends of bones, anybody know what the name of the ends of bones are? I'm going to find out in a minute. Epiphysis, ends, diaphysis, the long part. Now, bones that go across each other, it would be nice if they had a nice, slick, slippery surface to slide over each other rather than grind across each other. So we're going to find this type of cartilage, hyaline cartilage, at the ends of these big, long bones that glide across each other. We're also going to talk more about those synovial cavities when we discuss the skeleton. And then we see something called fibrocartilage. Fibrocartilage has more what in it than some of those other guys? More fibers. So it's a little bit stiffer. So we're going to find it in places where we need a tiny bit of movement, but not a lot of movement. This pubic symphysis and the intervertebral discs. I think we talked a little bit about that when I described fibrocartilage to you in chapter 4. So we'll see those guys associated with the skeleton. They're very important parts of the skeleton because we have to have a little give there. Bones, once you reach adulthood, they stop growing. True or false? False. Yeah. Your skeleton today will not be your skeleton in 5 years. It will be totally new. They grow. And then we do what? Break them down. So they're constantly growing and being broken down. Yes? And that's what they talk about under the growth of cartilage, and appositional growth is described for you as well. So they're constantly growing and being broken down. What are they being broken down for? What do we use bone for? We store a lot of our very important ions that we're going to use for a bunch of different chemical reactions in the body. As we go through this course, you'll see calcium coming up quite a bit. When we talk about the nervous system, calcium's going to come into play again. When we talk about the muscular system, calcium's going to make another show. When we talk about blood, there's calcium again. When we talk about the cascade of clotting. So these ions are very important for many, many different chemical reactions that go on in the body. And we need a constant supply of them. Not only calcium, but things like magnesium and phosphorus are also a very important part of the bone matrix. Remember, this is what kind of tissue again? Connective tissue. And how do we describe connective tissue? Some kind of matrix with cells inside of it. Lots of fibers. When we talked about ground substances in our description of connective tissue, we're going to have a lot of it in osseous tissue. So, first thing the book goes into is classification of bones. Again, two major divisions of the skeleton. We have axial, we have appendicular. And then we describe the bones according to shape. So they can be classified according to the shape of them. Long bones, Nope. Long bones are what? Long. They're longer than they are wide. Okay? Then we have something called a short bone. What are those? Short, kind of cube-shaped. When we talk about these guys here, you have 8 of them, believe it or not, in your wrist, and you have 7 of them in your feet, and that allows you to do stuff like this. We talk about short bones. We have other bones that don't articulate with other bones in the skeleton. They're actually hanging there sort of in limbo, not really, suspended in ligaments or tendons. And those are referred to as sesamoid bones. So this one here, can't do it. It wiggles back and forth, right? That's the patella. It's wedged in a very large something that attaches bone to bone. What attaches bone to bone? Ligaments. That's kind of wedged in there. It helps to reduce friction so that the knee can bend like it does. So that's a sesamoid bone or a short bone. The other classification is flat bone. A good example is your sternum. Flat. Another one? Another one. There's a whole bunch of them we're going to find out. The cranium. Flat bone. It's like a bone sandwich. We'll talk about in a minute. That would probably be classified as an irregular bone. And then the last one is a regular bone. Anything that doesn't fall nicely into those categories, like your vertebrae, have a bunch of weird little shapes to them. So we call them irregular bones. So what are the bones for? Function of bone in your textbook. Support. What would you be without your skeleton? Kind of like a puddle, right? Protection. If I didn't have what, that I would have just incurred brain damage. Yeah, I would have killed some neurons, wouldn't I? So, cranium, thoracic cavity for protection. Would I be able to move without my bones? And not very quickly, would I? So I can move a lot faster with my lever system, my skeleton, for my muscles to pull on so I can move faster. So they are important for movement in the human body. Really important for mineral storage. As we discussed just a moment ago, calcium. Not only calcium, but magnesium and phosphorus are examples of very important minerals stored in bone. The other thing we store in bone are chemicals called growth factors. And growth factors are going to help with what? Growth, yes. Extremely important place for hematopoiesis to take place. And that's a fancy way of saying what? Making blood. Making blood. Inside bone, we're going to find the stem cells, the original cells that will eventually become all of the cells we're going to discuss in your blood. All of the 5 different white blood cells, red blood cells, and fragments of cells called platelets all originate from bone. We also, believe it or not, store fat in our bones. So in that long bone, the diaphysis, we're going to find a big cavity in the center. And guess what's in there? Bone marrow. Anybody ever go and get their dog one of those marrow bones at I go to the butcher and get them because my dog's really spoiled. Loving those bones. Make a great soup, right? That's fat in there. So that's yellow bone marrow. At the ends of bones, that's where we're going to find the blood cell forming groups of cells in the red bone marrow. And then hormone production. Bones produce chemicals that are going to help regulate bone formation. Structure. There's 2 major types of bone that we're going to find in our bodies. We have something called compact bone, and that's the hardest stuff. And then we also have something called spongy bone. Now, it's still hard. If I look at it closely, it looks like a sponge. If you ever get bored, go home and look at your sponge. It's a whole bunch of sponge-like material. You know, hey, I want to pass the time in good ways, with little holes. So when we look at spongy bone, that's why it got its name, because it looks like a sponge. Those holes are important. Those holes are going to house things like red bone marrow. So spongy bone, or diploe, you'll see the term used, can also be found as part of our skeleton as well. So we are going to find combinations of compact and spongy bone throughout the skeleton. If you look on page, I don't know why I don't have an overhead of it, page 177, figure 6.3, you'll see an up close and personal of spongy bone, and then we see a part of the skull removed, a flat bone, which is basically like a bone sandwich, where we have compact bone on either end and spongy bone in the middle. So this is a long bone. So let's talk about some of the terminology described in your textbook using the diagram of the long bone. So long bone also has a combination of compact bone and spongy bone. So we're taking a little chunk out and bringing it out here and blowing it up of the proximal end of the bone, the epiphysis. This bone, does anybody know what it is? It's a humerus. So, nobody got that. Chuckled at that. They're all asleep. The proximal end would be what? This is my humerus right here. Where's the proximal end? Right? Closest to the midline. Where's the distal end? Here's where that, remember that language you got to know? You got to know it a lot for this. Distal end would be, the ends are the, of long bones, epiphysis. The long part of the long bone is the diaphysis. So again, long bones, short bones, regular bones, combinations of compact and spongy bone. Now, there's a layer of membrane that covers all of your bones. Bone is living. Even though it's hard, it's living. There's living cells in there, and what do living cells need? They need blood supply. They need nutrients brought to them. They need to get rid of waste products from metabolism. So what we have is a very extensive blood supply, believe it or not, in all of our bones. And what's going to help hold that blood supply in place and allow it to perforate the bone is this wonderful membrane. The membrane is called the periosteum. Periosteum. Peri means what? Around the what? Osteo. And that's osseous tissue, right? So the periosteum surrounds bone on the outside, and we also have some more osteum, but it's on the inside, so we call it what? Endosteum. That's going to help hold in place blood supply for all the bones. We're also in these membranes going to find the cells that will eventually create our bone matrix. So, bones, when you're little, thank goodness you're not born this size, right? Your mother's quite grateful for that. Your bones need to grow in what? Length. So we're going to talk a little bit in this chapter about where they originate from, cartilage. But once you are born, you have to grow your bones in length so you can reach adult size. And that is going to continue to happen until you reach your adult size bone growth in length at a place called the epiphysis. Now this bone is a mature bone, so that is no longer cartilage. That is called the epiphyseal line. But if I look at an x-ray of a very small child, it's going to look like all their bone ends are broken. Because that epiphyseal line in a skeleton that is still growing in length is called the epiphyseal plate. And it's not bone, it's what? It's cartilage. So the membranes are going to hold nutrient-bringing arteries in place. And when we look at bone in lab, we're going to see that it's not a solid thing. There's actually a bunch of holes in it. And what are the holes for? Huh? No? On the outside, little holes. Yeah, for arteries to pass in and out. Also, nervous system passes in and out. So, we're going to see holes, or we don't like to call them holes in science. God forbid, we have to give them a science word. Foramina. And there's going to be, on long bones, a couple of large foramina that we call the nutrient foramina. So, we have hematopoietic tissue that we also find in bone. And we will find that those cells, those stem cells that we're going to talk about when we talk about the blood chapter, we're going to find them in the epiphysis of long bones and in certain places with majority of spongy bone, and we find red bone marrow. So in the little holes created by the trabeculae formation of bone, and that's what we call that little sponge-looking bone formation, in the holes is where we're going to find red bone marrow. If we look at the diaphysis of the bone, we see another big cavity. Again, that's surrounded by the endosteum. And this is where we're going to find yellow bone marrow. Now, what's yellow bone marrow again? Most of it is fat. Okay? So 2 cavities, the medullary cavity in the diaphysis, kind of in the middle, with yellow bone marrow, and then the spongy bone at the epiphysis of long bones with red bone marrow. Bone is continuously growing. And do you know what causes bone to regenerate? Yeah, well, sometimes your need to store calcium is going to cause bone matrix to form. Believe it or not, I'm doing it right now. Standing. Tendons, ligaments pulling on bone. That pressure also causes your matrix to form. So if you sit around and watch SpongeBob all day, what are the chances that you're going to build more bone matrix? You always build it. You have to store it. But if you want to store it efficiently and have stronger bones, you have to what? Create some sort of pressure on that bone or skeleton. The pressure of muscles pulling on tendons to cause movements can also cause thickening areas in bone. So we're going to see, especially in lab when we discuss bones, that they're just not straight. They have special markings on them. Thicker areas where there's ligaments or tendons attached, holes or foramina where certain nutrient arteries or other things pass through. So we're also going to discuss, when we discuss this chapter, bone markings. And again, these markings are usually associated with either some sort of pull or thickened area or something sliding beside or through. We are going to look at those markings on page 180, table 6.1. And do you have to know all of these? Yes, you do. Holy crap. Tuberosity, crest, trochanter, line, tubercle, epicondyle, spine, and process. No. Projections that help to form a joint. And what's a joint? And I'm talking about the skeleton. Only one person got that. You guys really need coffee this morning. What's a joint? Yeah, where bones meet. Some sort of movement there, typically. So we have a head, a facet, a condyle, and a ramus. Depressions and openings. And typically, for example, when we look at the bones of the skull and we look at something called the temporal bone, it has a process that sticks out. That process meets another process that sticks out on a bone here called the zygomatic bone. And they form what we call the zygomatic arch. Now there's a space under there. What runs through it? I'll give you a hint. Yeah, the muscle that does what? Allows you to open and close your mouth. So we're going to see spaces or depressions in bones or holes in bones where things either slide beside it or slide through it. So we have a groove, a fissure, a foramen, a notch, a meatus, a sinus, and a fossa. All for your learning pleasure. These are all, again, bone markings that are associated with something else in and around the skeleton. They're also going to help you to identify bones and what might be near bones. And you'll talk lots more about those in lab. So, the next thing we're going to look at is microscopic anatomy. When you looked at tissues under the microscope. Oh yeah, no, you haven't done that yet. You're going to do that for the next 2 weeks in lab. Lucky you. You're going to be the queen and king of microscopy. If you don't know how to use a microscope now, you sure will after the next 2 lab classes. You're going to look at tissues. Pay close attention to osseous tissue. When you shove it under the microscope and have a peek, it's going to look like tree rings. Yeah, it's crazy looking. Because the way it grows is the cells that produce the matrix grow around their food source, just like a tree ring. So the center would be a food source of any given ring, and then the cells will secrete matrix around themselves and form tree rings almost around that food source. So this is compact bone, that's spongy bone, and we're going to have a look microscopically at compact bone. You should understand all of the terminology here. Know what an epiphysis and a diaphysis is, the medullary cavity, where spongy bone hangs out, and all of that good stuff. So now let's talk a little bit about the guys that actually form bone. We have several different types of cells that are responsible for forming and maintaining bone. They all come, or I shouldn't say all come, many of them are associated with what we call the osteogenic stem cell. Anytime you hear that term stem cell, that's usually some precursor cell to somebody else. We're going to hear that term again when we talk about blood, when we talk about the hematopoietic stem cell. So, osteogenic cells are cells that will eventually mature to form the cells that are going to form bone. When I need to make more bone, and what do you think is going to signal me to make more bone?
Pulling of the muscle.
Yeah, when I apply pressures, right? Or when I have to do what? Say I went to Friendly's and had one of those big, giant sundaes. Lots of ice cream. Well, yeah, when I intake some calcium and I need a place to put it, this might be some of the things that help me generate bone. Those are the cells that are going to be signaled by different chemicals, hormone signals throughout the body to start to change. And they start to change into something called an osteoblast. The osteoblast is a cell that will start pulling that calcium out of the circulatory system from its food source and doing what with it? Do you know? Well, it hangs out in a matrix. Who do you think is going to make the matrix? The matrix is made out of calcium and phosphorus and magnesium. That cell, the osteoblast, is going to pull that calcium out and then spit it out around itself. And that's where the tree ring growth begins. That's the matrix that bone sits in. And it's produced by the osteoblast. So that's why it's described as the matrix synthesizing cell responsible for bone growth. Yes? Now, at some point, and according to the textbook, 90% of bone protein includes also fibers, collagen, calcium-binding proteins we call osteoid. So again, bone is also containing organic material. It's a living thing. And osteoblasts form those tree rings or bone matrix. At some point, we don't want to close ourselves off totally from our food source as an osteoblast. So at some point, I'm going to stop producing that matrix, and I'm just going to hang out and do my cell thing. When I get to that point, we're going to call me an osteocyte. And osteocytes are what we call bone maintaining cells. They change a little bit, don't they? They grow these little projections or arms. And we're going to see them in the lacunae when we look at this histology of bone. That term should be familiar, right? You heard it in chapter 4, right? What's a lacunae? It's a space in connective tissue where bone lives, where cells live, right? So when osteocyte comes into play, we're going to be hanging out in the lacunae and we're going to be maintaining bone. So sometimes they refer to as the bone maintaining cells. So we're constantly growing bone, right? So why don't we have super huge, gigantic bones? They break down. So we're constantly building them and breaking them down. Breaking them down to release what? Yeah, all those wonderful things we stored from that great Sunday we got at Friendly's. And who's going to help me do that? This guy here. Another cell we'll see associated with bone is something called an osteoclast. An osteoclast actually used to be somebody else until I told it to go break down bone with hormones. And when do you think I would tell it to go break down bone with hormones? When I need what? When I need calcium, right? Remember, that's what's stored in the matrix of growing bones. So the signal for that guy to come into play would be what? Decreased blood calcium levels. So who didn't eat breakfast this morning? Still have a few holdouts on the breakfast. Do you think your calcium levels might be low? So what do you think you might be doing now? You're not dying. You're not dying. We're good at taking care of that. But what do you think, besides your insulin and all your glucagon and all those other things we've already talked about, who else do you think is in trying to get some bone matrix from you so they can increase those calcium levels? Osteoclast. Osteoclast used to be, before they got the signal, monocytes. Monocytes hang out in the circulatory system. But when they get the signal, a hormonal signal, to increase calcium levels, and we're going to talk about that when we talk about the endocrine system, that cell's going to morph into an osteoclast, squeeze out of the circulatory system, and go start breaking down bone matrix. No. I don't know what the heck that is. It looks like it, doesn't it? I don't think they have that many. Oh, maybe they come together and do it. So osteoclasts, bone breaking cells for reabsorption of bone matrix. Yes? So know those cell types, know what they do, know where they come from. Oh, there's my little diagram. And we're going to see combinations of bone in flat bones, spongy bone, compact bone, and they're all formed from these substances. When we look at the arrangement of bone, we see something very similar to a really, really strong rope. And that really, really strong rope is made up of a combination of fibers that go in different directions. So if you ever look at a big, huge rope that's holding on a large ship to the pier, do all the fibers in the rope go in the same direction? What would happen if they did? Yeah, it would snap. There's not enough strength there. It's not going to hold enough weight like your bones have to do on a daily basis, right? So what we see is an arrangement of different layers in that compact bone. And we see that the fibers in the matrix of this connective tissue are going to go in many different directions. That's going to provide strength. Strength so we can take a lot of weight. When we talk about those tree rings, those growth rings, we're going to refer to them as osteons. So if I take a close-up and personal of any piece of compact bone, and this is what you're going to see when you look at bone under the microscope, you're going to see that it's a series of these growth rings that actually come from or form around some sort of nutrient grouping. So there's a space with these blue and red tubes, and there's a yellow tube in there too. What's the yellow tube? Nerves. Are there nerves in your bones? Anybody ever break a bone before?
Oh, yeah.
Did it hurt? Yeah. So we also have the nervous system that's part of the skeletal system that runs through these spaces that provide nutrients for the cells. So again, they're going to grow in these little growth ring-like compartments around any given group of tubes or nutrients. These are called osteons. Sometimes they're referred to as Haversian systems because guess what they call this canal or space? It's called the Haversian canal or central canal. And that's where we're going to find blood supply. So as we look at bone growth, it's centered around the central canal of a group of blood vessels, and then the matrix forms around that in a growth ring-like formation. Each osteon is several different rings. And remember, those rings will go in different directions to provide strength for the bone. So I used to show this really old movie way back in the day, where they took a femur out of a human. Well, I think the human was dead before they got the femur, hopefully. And they balanced a Volkswagen on it. And did it break? Nope. So that's lots and lots of pressure that those bones can take because of this very special arrangement of compact bone. So we call those rings that grow away from their food source lamellae. So let's go through the terms we have to understand for the histology of bone. Central canal or Haversian canal. Those growth rings called lamellae create something called an osteon. An osteon is basically a group of lamellae around one single food source or central canal. The cells themselves are housed in little spaces inside those growth rings. So if we look down here in the diagram, we see these yellow things are osteo what? Sites. These are bone maintaining cells now. Who made the rings? Who made the matrix? Osteoblasts. When they're hanging out like this, they're osteocytes. And they look different, don't they? They have these little projections. The projections are so they can get to their food. Remember, this is all bathed in liquid, so things are all floating in and out of this whole thing. Their food source is here. So how does this guy get food? Yeah, it's going to go through these tiny little canals. The little canals are called canaliculi. So when we look at ground bone, it's composed of a food source, that central canal, with lamellae that grow around it, and lacunae housing osteocytes, with canaliculi, little canals going towards the food source. Yes? That periosteum, remember, is going to help hold stuff in place. And we have these little fibers. If you've ever eaten chicken, like roasted chicken, Anybody like to gnaw on the bones?
I do.
Yeah. And sometimes that little membrane, it looks like there's little fibers that hold the those are called Sharpie's fibers. Everybody's going, ew, come on. I love roasted chicken. So that periosteum is held on by those little Sharpie's fibers. Remember, there's an endosteum, a periosteum. This is where we see bone growth happening. This is where we're going to find our buddies, the osteoblasts. And this is how all of these tree rings are going to start forming. Compact bone has the same type of formation, but it's just not as highly organized. So we're still going to have the same things in compact bone, but we are not going to see them as highly organized as we do in, excuse me, did I say spongy bone? Same thing in same type of formation, not as highly organized in the trabeculae. So we'll see that lattice formation rather than this real tight formation. In order to get blood supply to everybody, we have to have those Haversian canals, but then we also have to have a connection from the side. So we have Volkmann's canals, the canals that come in from the side or go horizontally in bone. The ones that go longitudinally in bone are called what? Those are the central canals or Haversian canals. Correct. Somebody found them and said, oh, I'm going to name them after myself. So, Volkmann's canals come in horizontally. Haversian canals longitudinally. Both will contain blood supply. Again, take a look under the microscope. When you look under the microscope, this is what you're going to see. Here's the central canal, the lamellae growing around it. These little black blurbs are the osteocytes, and these tiny little black lines going towards the center are the canaliculi. So, spongy bone is not going to be as thick and going to form extensions called trabeculae. So what's bone made of? It comes from cartilage. Bone, osseous tissue, is made of a lot of organic compounds, believe it or not. Fibers, collagen, a protein and substance, and a lot of the formation of matrix. All of these organic substances are called osteoid. Now, it's also got quite a few inorganic substances. Does that mean they're less important just because they're inorganic? No, but they're harder. So we see terms like hydroxyapatites or mineral salts. That's going to provide that hardness to bone. When you die, do your bones die? Yes, they do. But why are they left behind for so many more years than you or all the other organic material in your body? Because they're very high in inorganic substances, so it takes them a lot longer to deteriorate. Well, a little bit different terminology. That's molecular degeneration, atomic generation. But yeah, it's just a harder substances. It takes longer for it to degrade.
That mineral salts is the bone salts that chapter 4.
Yep. Bone salts, mineral salts, the hard stuff. So, how does bone develop? The process is called ossification or osteogenesis, the formation of bone. And bone comes from cartilage. Oh my goodness, 1, 2, 3 steps. Wouldn't that be a lovely little essay question on your next exam? So this diagram here is a diagram that describes something called what? Anybody? What is this process called? It's called ossification, but it's coming from a membrane. So what do we call it? Intramembranous ossification. You can see it on page 185 in your textbook. So in the beginning, there is no bone, right? So your one cell, you come from one cell, is going to start reproducing itself. Yes? No, formation of a bone is called ossification. Now there's two ways to form bone. This way, intramembranous ossification, and then we also have something called endochondral ossification. So right now we're describing what? Intramembranous ossification. That makes sense? So ossification making bone. We can make it from membranes or we can make it from cartilage. Yes? So in the beginning, we're no cartilage. We have to make cartilage, don't we? So our cells start to cluster. Remember, you come from one cell. And as your cell reproduces its stuff, it's going to start to differentiate. And eventually we'll see membrane form. From that membrane will arise the next group of cells called osteoblasts. And we know what osteoblasts do for a living, right? They start making bone matrix. So in the beginning, ossification centers will appear in membranes, and the membrane, that background membrane, is called the mesenchyme. And we'll start to see the first bones form. So they start in a centrally located area, and they start producing what? What do osteoblasts do for a living? Yeah, they start to produce osteoid. They start to produce that thing, that matrix that's going to start calcification. So in step 2, we see osteoid is secreted within the fibrous membrane and starts to calcify. So once that calcification starts, everybody can sort of build on that. Sometimes it's referred to as the calcification center of a bone. The cells that are making this will eventually sort of trap themselves inside this osteoid. And what are they going to become after that? That's when we start to see the first osteocytes on board. The other thing that this group of ossifying cells needs is a blood supply. So in step 3, we start to see the formation of what looks very much like trabeculae or spongy bone in the beginning. This allows us to prepare the bone for blood supply formation. So in step 3, we start seeing blood supply being formed throughout these little holes or trabeculae in the beginning bone. By step 4, we're going to start to create stronger and stronger bone. So we're going to start to see that osteon formation. We're going to start to see those lamellae start to form. We're going to start to see Haversian canals and perforating canals. So we're going to continue to form bone, thicken bone, so that we can eventually have a series of what look very much like flat bones in the skull, with that outside plate of compact bone in that diploly spongy bone cavity. So the beginning bones all look like flat bones in intramembranous ossification. You with me? So that would be a nice essay question. Now the other essay question that might also be nice from this chapter is the continuing to grow those bones big. And now we start to see what coming into play? Now we start to see that cartilage. Very similar to hyaline cartilage, at the ends of bones, we start to see some cartilage coming into play. So now with cartilage, I have more strength. Now I can actually form a nice long bone. This type of bone formation is called endochondral ossification. And in step 1, we start to see what we call a bone collar form. So we're starting to form from cartilage a long bone. And that bone collar is going to provide us with strength so we can do that as cells. So bone collar has to form before we start the formation of long bone. The other thing that's going to start to happen is I kind of hollow out the center. So cartilage in the center will start to hollow out to develop what? That medullary cavity in a long bone. By the time we hit step number 3, we start to see what? That periosteum. And what's that going to do for us? Yeah, it's going to line, it's going to provide support, it's going to sort of give us support so we can continue to grow in length on the outside. We'll also see that formation happening on the inside of those cavities we just formed. Again, that one nutrient artery, that's the beginning. We're going to end up with a lot more, but that one nutrient artery is then going to branch tremendously once it enters the cell. So at step 4, we start to see elongation of the bone. And as we go along in the long bone formation, we'll see more and more bone forming in the center and moving its way out. The ends of the epiphyses will see a lot of cartilage in step 4 still present. But in step 4, we'll also start to see a second ossification center form in the epiphyses of bones to create the ends of bones. By step 5, we have epiphyses, diaphyses, but we still have to grow in length. So we're going to continue to grow in length, replace cartilage or form cartilage, then replace it with bone in the epiphyseal plate, which in that mature bone, what did we call it? The epiphyseal line, because in you, you're all done growing, right? I think everybody in this room's done growing. Yep. And a lot of younger kids get breaks like that. At that epiphyseal break off. We call it, we give it a term in our book. So the epiphyseal plate is cartilage, and that's where we'll continue to see growth in length in long bones. So 2 types of ossification can take place to grow bones. We can have intramembranous ossification, and we can have endochondral ossification. You should be able to know the difference and answer an awesome essay question to that effect. So bones will continue to grow in length. And if we look at them under the microscope, we can see areas in that epiphyseal plate where bone continuously is growing. And we'll see different zones of growth continuously occurring. In the resting stage versus the ossification zone, we see cells performing differently. New bone is constantly being formed in the ossification zone. Calcification zone is where the matrix is formed. The cartilage cells will sort of die out, and we'll see the matrix of bone. Older cartilage cells enlarge in the hypertrophic or hypertrophic zone. And then cartilage cells undergo mitosis in the proliferation zone. So all bones growing in length, if we look at it microscopically, we'll see these different zones of growth. Bones will constantly grow in width or thickness. So even when you're done growing bones in length, you will always continuously grow your bones. So throughout your entire life, bone growth is regulated by hormones in your body. What happens when I start breaking bone matrix down faster than I can make it? Yeah, you start to get weaker bones. Give me a term that you might know. Probably all of you have heard it. Osteoporosis. Do you know what that means? Porous bones, holy bones.
Breaks down, makes it hollow.
Well, you're breaking it down faster than you're making it. So bones are constantly remodeling themselves. So the next section of your book talks about bone homeostasis, remodeling and repair. So you're constantly storing, making lamellae, and breaking it down. You're constantly depositing bone material. And that's what they talk about under bone deposit. That osteoid is constantly being made. And the osteoclasts are going to allow you to break it down and reabsorb it. This is going to help release calcium stores, magnesium stores, phosphorus stores for you to use. So that's what they talk about under bone reabsorption. Who's going to help control or regulate the rate at which you store and break down bone? Well, that's your good old hormones. You have part of your endocrine system called the parathyroid and the thyroid gland. And those guys are going to help regulate bone matrix storing and breaking down with some hormones called parathyroid hormone and calcitonin. Now, parathyroid hormone, secreted by the parathyroid gland, is going to help me do what? Here's an imbalance. What is that called, by the way? Homeostasis controlled by what? What is that a picture of? What kind of mechanism? Negative feedback mechanism, yes! So we have an imbalance. Calcium starts to fall in our blood. You didn't eat breakfast this morning. That means you're going to die. No. When calcium levels start to go down, that's going to give a signal to the parathyroid glands. The parathyroid glands are going to release their hormone. Luckily, it's called after the gland in which it secreted parathyroid hormone. When parathyroid hormone starts to increase, that's going to be the signal to those osteoclast guys to mass and go do what? Start to break down bone matrix. When bone matrix is broken down and released into the circulatory system, what's going to happen to calcium levels? They're going to come back up. Homeostasis will be achieved, and that's how we regulate negative feedback. Calcitonin, thyroid, opposite. But basically what happens is once you get your levels back, what are we going to stop releasing? This hormone. Okay? So that negative feedback mechanism is going to help keep calcium levels in place. Calcitonin appears to be a hormone in the search of function. Calcitonin has the opposite effect, but we don't see it doing that necessarily all the time. Yeah, so if calcium levels go up, what do I have to do now? Do I have to break bone down when I go to Friendly's and eat that sundae? What do I do? Now I have to store it. Well, who needs a signal? Not osteoclasts. Who's the other cell players in osteoblasts? To do what? Osteoblasts need to pull that excess calcium out of the circulatory system and create bone matrix. So some imbalances related to bone, might be related to calcium levels. Not enough calcium in your diet. How do you get calcium in your diet? Eat some Tums. No. Tums will get calcium in your diet, but that's good. You'll just pee it out. Drink some milk, you'll just pee that out too. How do you get calcium into your circulatory system? You have to absorb it, don't you? Not just calcium do you need to bring into the digestive system. Yeah, you also need some help absorbing. So vitamin D is also necessary. If you look at milk, cow's milk, by the way, we were not meant to drink cow's milk. Cow's milk is to make little baby cows into big, huge cows. It's not for humans. No, no, no. Yes? The dairy industry has us brainwashed into thinking that if we don't drink milk, our bones will fall apart. But milk is not the only place to get calcium from. Yes? Spinach, believe it or not, you can get calcium from. So there's a whole bunch of other sources. But remember, cow's milk doesn't have vitamin D in it. They have to add it. It's added to the stuff that you buy at the supermarket. So you need vitamin D to absorb it into your circulatory system. And all right, we'll pick up with mechanical response and fractures and all that good stuff. We're also going to skip right into chapter 7. So I guarantee you, why don't we do this? Let's have a quiz on Thursday, chapter 6. I guarantee you I'm also going to finish chapter 7 on Thursday as well. Do you know what that means?
Your machine. Your machine.
No, but did you look at your schedule?
We don't have school Tuesday, right?
You don't have school Tuesday, but guess what's coming up? Yeah.
4, 6, 7, and 8, though. Are you going over 8?
4, 6, 7, and 8. That's coming up. Okay? So we...
Over 8, though, before the test.
I'll go over it. Well, it's not going to be that week. It's going to be the week after. Oh, clickers! Don't worry, you took a quiz. We'll go from that. Probably not.